ahead and start, my friends. Um, like we said yesterday, I'm not going to go, guys, and refer to all these tables that we did yesterday because we did that yesterday, right? So you're going to hear me talking about table 220.12. Everybody knows what we did on 220.12. When you graduate from here, you should know how to use table 220.12. Okay, here's the apartment that we have. Typical apartments. Carrie's not here today, but they work on an apartment. Apartment building, residential load calculation. We have 30 units. Everybody knows what you guys have a copy of it. 30 units. So it's an apartment, 30-unit apartment building. The unit, the square foot of each unit is 1,000. Cool, 1,000. The voltage that I'm feeding this baby is 240/120. Each apartment has an AC unit, 30 amps at 240. Heating of 10 kW, electrical heat at 240, range of 16.5 kW, also at 240, and dryer of 6.5 kVA, your dryer at 240, and a garbage disposal of 1.5. We have a dishwasher 1.2. We have a water heater 240 at 5 kVA, and a pump of 7.5 horsepower. A pump of 7.5 horsepower. Any question, guys, about what's in this apartment building? Cool? Typical. Now, if there's any other things, guys, what do? You keep adding them. You just keep adding them. So here's the copy for you, bud. So this is where, this is any question before we go ahead and solve this problem. So we have an apartment building with all this requirement in it, and we are required to find the service. What's my requirement? I'm required to find the service, disconnect the panel that feed the panel, the overcome protection device, as well as the conductors. Cool? Any questions, Andrew, Adam? Any comments, any questions? You will have a problem exactly like this, guys, on the test. And when you on the test, because of all this calculation, have a cheat sheet that tells you step by step how to do it. I don't care as long as you know how to do it. Cool? All right. Everybody knows what we have. So we're going to go follow the steps that we did yesterday, guys. We're going to go follow the steps that we did and solving them. So I'm ahead of you. I'm going to give you some time to recoup here. And I need somebody with a calculator to help me go through this one. So for this apartment building, the first thing we need to do is the general lights. Does that sound familiar to you? That's from the sheet that we did yesterday. My general lights, and my general lights, I have my general lights and receptacle for this apartment building. This is coming from table 220.12. 220.12, cool? Table 220.12. Anybody can tell me what's the volt amp for this apartment building? No, the volt amp per square foot for a dwelling. 3. So you first of all, you take the 3, then you multiply it by 1,000, then you multiply it by 30. Any question why we multiply by 30? Any question why we multiply by 30? We have 30 units. We have 30 units. Cool? That's as easy as, now remember, we are sizing only for the service. We're sizing only for the service now. The service, the main big fat building. Cool? The main big fat building. Any question, guys, about this? Everybody's okay with this? 30 units, 1,000 square foot each, multiplied by 3. And if you anybody an answer? 90 kVA. Done. So 90 kVA. Any comments? Any questions about this? Is it wrong or no? 90 kVA. Okay. Any comments? Any questions about this? Joe, you need this one, right? So we have an apartment building. Multiply it, that'll get you 90, not 96, 90 kVA. Any comments, any questions about this? Straightforward, right? You take the volt amp, multiply by the square foot of the building, multiply how many units you have. Okay, let's go to the second one. Small appliances, branch circuits. 220.52a. What does it say? How many small appliances, guys, we have? 2. Okay, so 2 small appliances multiplied. What's the allowance for each small appliances circuit? 1,500. from now on we talk KVA. So in KVA language, what is it? 1.5. 1.5 K multiply this one by, how many units do we have? 30 units. Thank you. So everybody knows where the 30 is coming from because we have 30 units. Answer. What's the answer? 90. Thank you. 99 kVA. 90 kVA. Cool. See how nice and easy and piece of cake is that? You can't get it less than that, huh? Any comments, any question, guys? Why did I skip number 2? Adam, why did I skip number 2? Because the sheet that we have skipped number 2. Number 2, guys, used to find how many branch circuits do I need in an apartment building, and it used to confuse the students. So I just got rid of number 2. So that there is no step 2. Everybody's okay with that? There's no step 2. Okay. All right. Any comments, any questions about that? See how easy and piece of cake is that? Shall we do the laundry? Okay. How many circuits, laundry, assuming that we have laundry in every apartment. If you don't have laundry in every apartment, then you don't have to do that. We're assuming we have a laundry, meaning a washing machine in every apartment. Okay? So, Aaron, my friend, the assumption is 1 circuit for every apartment multiplied by, what's the allowance for that particular circuit? 1500. In the lingo of KVA, 1.5 K multiplied by 30. Why 30? 30 units. If the test guys showed you 20 units, would you multiply by 30? That's a dumb question, right? So what's the answer? Thank you. 45 kVA. 45 kVA. Any questions, any comments? That's this example, Joe, follows exactly the sheet that I walked you guys through yesterday. But I want to do one by hand, and you guys will do it. We walked you through the Excel yesterday, and we're going to do one by hand because we want to emphasize that you know how to do it for an apartment. And I believe some of you guys have done it for a house before, right? So we're just expanding it to an apartment. Any questions, any comments? Let me know when you guys are done. Cool? You're already plugging into your computer. Absolutely. On the test, I want you to do it by hand one time for me. Okay? Let me know when you guys are good. Okay. So we have... anybody can predict what step number 5 would be? Add them together. Add them together. Let me know when you guys are done, Joe. Aaron, you good? Okay. 225. Take it easy on us, man. It's Monday morning here. It's Tuesday morning. Is it Tuesday morning? Yeah. Our days are blending together. When you're having fun, it goes fast, huh? Okay. Let's go to the next step. The next step, my friend, is add 1, 3, and 4 together. So I'm going to go at them. So I have 90K, and another 90K, and a third 45K, and for a total of 225 kVA. If I did something wrong, please bring it to my attention. Any question about that? Add them up. I'm going to give you enough time to write that. Add them up. Add them up. I'll give you some time to write these steps. Add them up. Okay? Anybody can predict what the next step after we add them up would be? Apply the demand factor on them. We need to apply the demand factor because the code assumed that you and your neighbors in an apartment building of 30 units will not be using all the lights and all the receptacles fully at the same time, right? Highly unlikely, unless you put a bunch of teenagers in every apartment, turn all the lights on, plug every single outlet with a load in it, then guess what's going to happen? Your main will trip. Any comments, guys? Any questions about this? Okay, let's do the demand. Now from table 220.42, which we walked you guys through yesterday, so everybody should know where table 220.42, can I have thumbs up, Chad? We fully understand where this table is, okay? So we're gonna go and apply the demand factor. All right, so let's do the demand factor. From this table, it says you take the 225 kVA. Do the following demand on them. The first 3K, what do you need to do with them? Multiply them by 1, meaning leave them alone. You don't do anything with them, right? Okay, next. So that's it, when you apply the demand. Next, the first 117K, you multiply these by what? Like we said yesterday, 0.35, 35%. You multiply it by 35%. The first 117, right? Then after that, the remainder, guys, which is 225 minus 120, all of them are K's, and that will get you here, I don't know how much would that get you because I add them up. Anyone can give me this step, guys? Can you guys take 225 minus 120? That's easy, Chad. So that will give you 125, right? 105. I think I'm 105K. Then you multiply this number by what? 25%. By 25%. 0.25. I don't like the way we did the math on it. So I'm going to do it this way. I'm going to say you take the 225K minus 120K, get you 105, you multiply K, then you multiply this by 0.25. And then what do you do with them? Add them up. What do you do with them? You add them up. So I have 70.2 kVA. Anybody came up with something different?
Oh, yeah.
I need a second.
Good.
Second? Okay. So you add them up, that'll give me 70.2 kVA. I'm going to highlight this with black because that's the number that I'm going to be carrying later on. Can you guys put stars next to that boy? That's the number that you're going to be carrying downstream. So highlight it. That's the number they're going to be carrying downstream besides. 70.2 kVA. Do you see how all this 90, 90, 45? Imagine if you add these and you size the system based on this. Disaster. Can you guys see disaster in the air? So the demand factor will give you a much lower value. A much lower value. Okay. Any comments, any questions? Can I have thumbs up, Chad? We fully understand. Adam, my friend. Andrew. Brian. Okay. Good. So let's go to step number 7. What do you guys think step number 7 is? Ranges. Let's go to step number 7. Step number 7 is ranges. Table 220.55. Let's go do the range calculation. So I'm going to remind you, we have ranges. So we're going to go the following. I have how many ranges and what size? I have 16.5 kVA range, and how many of them do I have? 30. Okay. So let's see. I have 16.5 kVA, and I'm going to take them to table 220.55. I want to remind you I have 30 of them, so that will put me under which column? Which column am I going to be under? On the column C for 30. What's my demand for this? If you guys go there to this table, it will tell you have to have 15 plus 1 kVA for every, your demand, everybody's there? If your demand from this table will tell you, maybe we should flash that boy because it's an interesting.
15K plus 1K.
Plus 1 kV for every range. So let's go flash that boy, will you? Let me see if I can open my. So 15 kVA. So do you see, guys, how we mix all this load calculation all together? So, what? Okay, now why do I have to speak Greek here? Let me see here. Let's go file open. No, with this Windows. Come on, bud. It's cooking, 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 cooking. I hate it when it cooks too fast. All right, let's go open it. Desktop. Yeah, I should have opened my NEC code book. Do you guys want a 2012 or 20? You don't want. There you go. 2011 or 2014? 2011 is good enough. Okay, 2014 is already there, man. The copy of it. All right, let's go all the way to here. Okay, can I guys get you to this point here? So we have 30. We have 30 of them. 30 will tell you this, right? So what does 30 means? I have 15 plus 1 kVA, kW for each one of them. So that will be 15 plus 1 times 30. And that will get you what? 45K. Any question about this? Everybody knows that? Where would get the 25? Okay, let's take a snapshot of this one, so because you guys are cool. All right, so we got snapshot of that boy. So let's go back and take full screen here. So let's go. So everybody knows where the 45 came to be, right? It's 45 kW, which is equivalent to kVA. Cool. But there's one little problem, guys. Also, note number 1 will tell you if then you have to increase this value, 1 kW, you have to increase it 5% for every 1 kW more than 12. You guys remember that one? From note number 1, right under the table. Note number 1, right under the table. So if you come over here, right here, this note, if it's higher, then you have to increase it, shall be increased by 5%. Everybody can see that? Here's where we're doing right now. This note, based on this note, right here. Cool? Everybody's there? Okay, so that's what we're going to do based on this note. Oops, not Skype, Chad. We're not going to Skype people today. All right, so let's go ahead. Everybody knows we got that one. Then, the next step that you need to do is you need to take the 16.5K minus 12K. That will get you what? 4.5 kW, and that approximates to 5 kW, right? Because 0.5 goes up. Then your next standard, right? It's going to be for every kW you multiply it by 5%. So that will give you an increase of 25%. Everything that I'm writing right, guys, now is from note number 1, right? And then finally, you're going to take 1.25 and multiply it by 45 kW, and that'll get you a healthy 56. I have 56.3 kVA. Anybody has a second on that?
56.25. What are you rounding up?
56 point what?
56.25K.
56.25, rounded up to 56.3. Is that okay? Yep. All right, so this is the number that you guys are going to take down. Everyone that I highlight and put stars next to it, that's the one that's going to be carried for that step. Let me repeat myself one more time. First, based on the kVA and the number, under C you get 45 kW. Then, and because the size is more than 12, if it's 12 or less, you're done. More than 12, then you have to subtract 12 from it and find how far are you away from 12. And 4.5 will approximate to what? 5 kW. Then you take your 5 kW, multiply by 5, will get you an increase of 25. What that tells you is you need to up the 45 kW 25%. How do you up a number 25%? You multiply it by 1.25, right? Any question, guys, about these steps? So here you go. Here's range calculation embedded directly into the service calculation. Can you have a thumbs up, Andrew, my friend, and Adam, and Joe? Any question about this step? Any question about this step? Cool. So piece of cake, right? So you have to know how to use the table 220.55, right? Okay, move on. Where's Aaron? Move on. Am I going too fast? No? Too slow? Okay, so here's where we got this stuff from. Okay, now the next step is dryers. The next step, my friends, is dryer times 220.54. For 220.54, here's my dryers. Anybody can remember what the size of the dryers I gave you guys? 6.5. 6.5. So here's what you're going to do. I have 6.5 kVA. You're going to take this boy to table 220.54 for 30 of them, right? Remember, there's 30 of them. You're going to get the following. Okay? So there's a couple of calculations that you have to do here. Let's go do the calculation. There's a calculation that you have to do. The calculation goes as this. It says 35% minus 0.5 multiplied by, how many ranges do I have? 30 minus 23, don't ask me where the math came to be. And that will equal 35% minus 0.5 times 7. And I'm doing it like baby steps here. 35% minus 3.5%, and that will equal to 31.5%. All this mess to calculate the derating factor. You have to calculate the derating factor. Okay, so for this one, let me flash. So let me flash and show you guys where all this mess came to be. Okay, so let's go to the derating factor for kitchen dwelling. Non-dwelling, no, we don't want this one. 54. Where did 54 go to be? Did I? Okay, optional. No, I think we went too far. Okay. Okay, demand factor for household electric clothes dryers. Here's where we are. We're at this table here. Okay, the dryers. And I have 30 of them. If I have 30 guys, then I'm where? I'm right here. Everybody can see that? So then it says 35 minus 0.5 multiplied by a dryer, the number of the dryer exceeding 23. So I have 30 minus 23. You see where this equation came to be? 35, you start with 35, then you take the number of dryers that exceed 23 and cut them by half, then subtract them from 35. Any question, guys, about using this table? Any question about using this table? If you can see, we're right in here. It says 35, no problem, Chad. Then minus 0.5% for each dryer exceeding 23. How do you do this in a math language? You do this in a math language by having 35% minus 0.5 multiplied by brackets. How many dryers do I have in my example? 30 minus the number 23, that magic number, and you do the math for this. I hope all of us know how to do the math. You do the brackets first, then you multiply, then you subtract the total from 35. Any question, guys, about how this came to be? Can I have thumbs up, Chad? We fully understand that one. Okay. So with this, here's where the 31.5 came to be, right? Everybody knows where the 31.5 came to be. 31.5. Okay, all right, now we're done. Now the last step, the last step that I'm going to be using here, the last step that I'm going to be using is I have 6.5 kVA, multiply this by 30. Why 30? Multiply by the rating factor of 0.315, and that will get you a healthy
61, 61.425.
Yeah. So that will get you a healthy 61.4 kVA. Anybody, any second on that?
Yep.
All right. And that's the number, the magic number that I highlighted, and you guys have to carry. That's the derating factor for all the dryers. Any question, guys? Can you guys see it? You cut them by 31%. Can you imagine if you size for all of them together, how big of a service you're going to come up with? I can't emphasize. Do you guys appreciate these tables? Everybody understand why these tables are there? Otherwise, the service would be bigger than this room. And they don't make a service bigger than this room, switchgear. If you add them up, look at that. If you multiply them all and then you cut them by 31%, down to 31% what they used to be, that's substantial. If I cut your salary where you work at 30 down to 31%, would you be happy? You'd be mad, right? So 31% down to 31% is a lot of derating, guys. Can I get you, Andrew, to understand the gravity of what we're doing? Okay, because this is what distinguish Adam between a designer and a drafter. Designers understand why are we doing what we're doing, to try to reduce the size of a service. Cool? Aaron, my friend, does it make sense? Really, the step-by-step here, these steps, Aaron, bring them to the test with you. I don't care, as long as you understand them and how to follow them. Otherwise, there's so much. Okay, I need thumbs up. Move on, Chad. Thumbs up. Okay, what do you guys next step do you think next step would be? What I did here for you guys, okay, what I did, I have another example just for the heck of the dryers to exercise the dryers, extra dryer example. 40 dryers at 5.5. That's extra, has nothing to do with it, with what we're doing. Let's do that one. Extra dryers, 40 extra dryers, and I have 40 of them. Okay, so if you guys remember how, again, this has nothing to do with it, our example. You take the 35%, subtract them by, if it's 40, 0.5% times 40 minus 23. Again, this is just to get you into the 40 dryer, has nothing to do with our example. 40 dryer, here's the size for them, right? This is the same example that we did, an extra one. Then, that will get you 35% minus 0.5% times 7. And then if you keep going down, 35%.
17.
Do you have to correct me? 17 minus 8.5%, thank you. And that will get you a healthy 26.5% derating factor. So we have to calculate the derating factor. Again, this has nothing to do with our service, just an extra example. Then the final one, you take the 40, multiply this one by 5.5K, multiply it by 26.5. Well, 26.5% turns into what? 0.265, and that will give me a healthy 58.3 kVA. I can't emphasize, this has nothing to do with our example. This is just an extra example how to do a dryer. Thumbs up, Chad. We know how to use dryers. 53. 58.3. Any second on that one, guys?
I came up with
Can-
53 degrees.
Anybody can second me or second him? Got mine? Okay. Two gentlemen agrees on.
No, we didn't know that. It's
0.265. Okay, again, this has nothing to do, please be aware, this has nothing to do with our example here. This is just an extra bonus for you. All right, let's continue with our example. Any question about that? Piece of cake, the dryers. Did you guys do dryer calculation with Ryman?
Yeah.
So this is not big deal for you. Okay, heat and cool, heat cool. Now we're gonna go to the next step. Step number 9 is heat cool. Okay, so let's go to the heat first. What was my heat? I have 10K for every apartment, which is 30, and 30 of them. That will give me a 300 kVA. Cool? Any question about that one? So for the heat cool, guys, here's the article that you can use for heat cool. And you have to basically you do the calculation at 100% for both of them and choose the largest load between the heat and the cools. 220.51, 440, 220.60. All these will tell you to do the calculation 100% and then pick the largest of the two. Okay, let's do the cool. What was the AC unit? I have the AC unit 30 amps each, multiply it by 240 volts, multiply it by 30, because there are 30 of them. I came up with 216, right? kVA. Cool? So then what do you need to do? So this is my heat. Then the next step is choose the largest of heat. Choose the largest of heat and cool. Okay, so what was the largest of the two? 300 kVA, which is the heaters. So what do we do with this one? We highlight it in black and we put stars next to it. Everybody knows why we highlight it and we put stars next to it, because we're going to carry it all the way to size the surface with it. Then all these numbers, that it becomes meaningless. That's the last number for this step. Can I have thumbs up, Chad? We fully understand this. Okay. So that's my heat. Any comments, guys? Any questions about the heat? So you pick the largest, 300 kVA, 216. Which one is the largest? We pick the largest, and we move on. Okay. I think there's a reason why I jumped into step number 11. What does step number 10 Zach says for you in your sheet? Net computed. Step number 10, guys, in the sheet that I gave you, honestly, is meaningless. Add them all up. We don't want to use that one because it doesn't add value to the calculation. So I skipped to step number 11. Everybody knows why I didn't do step number 10, because it just add them up, the stuff that I did. I want to wait until the end to add them up. So what I suggest, Jeff, maybe get rid of even step number 10 altogether in your sheet. Doesn't add any value to, doesn't really add any value to. Okay, can I thumbs up to move on, Chad? All right, so let's move to step number 11. Everybody knows why I jumped over 10. 10, based on our sheets, it really doesn't add value. Add them up. Okay, fasten in place appliances, Article 220.53. Okay, so I want my friend, what was the dishwasher size? 1.2K multiplied by how many of them do I have? 30. Okay, how about garbage disposal? 1.5K multiplied by how many of them? 30. Water heater, 5K multiplied how many? 30. Any question guys about these? And then you're going to add them up. Don't forget to add them up. Add them up, and that will get you 231 kVA. Okay? Then, that's step one. Then step two, demand. You have to demand. Demand. The demand, guys, in yours, it's step number 12. The demand in your step, the demand in yours was done in step number 12. I'm doing them all together here. Step number 12 was a demand in your sheet. I'm doing them all together. So what's the demand? I have 231K, multiply this one. What's the demand for all of them? Is it 0.75 or 0.7? What's the demand for 3 or more? Can somebody go to 220.53, just verify, is it 7.75? I have 0.75 from article 220.53, and I need somebody to verify this one, guys. What? Yes? Okay. And that will give me a healthy what? 173.3 kVA. This is when I go highlight this boy and put stars next to it, because I'm going to carry this boy all the way down.
Is that supposed to be 23K or
231? Right? 200, if you added 231. Thank you. 231. 231. Somehow my 2's are screwed up. Okay, 231 kVA. Make sense, Joe? Then you apply the demand to 0.75. Did you guys verify this at 0.75, Jeff? Okay, so that's the number they're going to carry for all these steps. I wrote here step number 12 in the sheet. So here's my advice for all of you guys. Darren, my friend, the steps that I said embedded here, I don't think there is no need for you to add them as a step. If you guys want to modify, you might have to do like step 12 is meaningless because we add them completely, we plug them into here as a demand. Okay. So, what's step number 13? Anybody knows what step number 13? What does it say, Zach? Okay, total computed load. Skip that one. Doesn't add any value to me, right? Because I'm going to add them way at the end. I'm going to add them way at the end. So I'm skipping step number 14, number 13. And I'm going to go all the way to step number 14. Everybody knows why I skipped number 13. It doesn't add anything to me at this moment. Just keep adding them up. I'm going to collect them individually, guys, and add them way at the end, one time, some lump sum them. So every step, you should be able to do the calculation for that step, demand it, find the final number for this step, and way at the end, add it up. Does that make sense? Okay, so let's talk about motors. Motors 250, 220.50, and Article 430 talk about motors. We take them at 100%, 125%. So how many motors do I have? The motors, guys, I have only one. By the way, I didn't tell you, the pump that I have is only one pump. It's not like 30 pumps. If there were 30 pumps, it's piece of cake. You do it, I'll show you how to do it. But I only have, can you guys write to yourself, it's only one motor, one pump. Okay? So if I have a one pump for the whole apartment at 75 horsepower. And if you guys go to table, go to table 430.248 under 240 volts, you're going to find the amps are 40 amps. You need to find the amps for it. So take the 75. I'm not 75. 7.5. It can't be 75. Can you guys add 7.5? Is it clear that 7.5 is the example that I gave you? Yeah, 7.5. So 7.5 at 240 under 430.248 will give you 40 amps. Can I have thumbs up, Chad? That's how we find the full load current. Piece of cake. Then I will do two steps in one. Since it's only one motor, the code says you add 25% on the largest motor. Which one is the largest motor? It's only one motor, Chad. So you add 25% on the largest motor. So you're going to take a 1.25, multiply it by 40, multiply it by, what's the voltage? 240 plus all other motors. What are the all other motors? Why do you think I put 0 here? Plus the volt amp of all other motors. Do I have any other motors? Volt amp for all other motors? None. So that will get you a healthy one. 12 kVA. Oops. 12 kVA. Oops. Not this, Chad. I need the same color. 12 kVA. So that's a demand for this step. The demand for this step. The demand for this step. 12 kVA. Now, if we have 10 motors, how would you do it? You take the first motor, 1.25 times 40 times 240. Then you take the rest of them, which is 9, times 240 times 40, and add them up. So you increase 25% on the fattest, fluffiest motor. Am I clear about this one, guys? Okay, so that's the one they're going to carry for this step. May I move to step number 15 and the final step? Step number 15 and the final step. So all these ones that you guys have seen, I highlighted in black and put stars next to them. Can you guys see that? All these steps that we had blacks next to them and from all the way through. Can you guys see that? So let's go here. So look at this step, step number 6. All these, I'm going to pull them in step number 15, pull them all together. Okay, here's step number 15. Step number 15 says the following. Okay, so step number 15 is total demand for lights. Look at this. Coming from step number 6 for lighting. What was the demand for light? Anybody can tell me? 70.2 K. Okay, let's go for step number 7. What was the demand for ranges? 56.3 K. Let's go to step number 8. What was the demand for dryers?
61.4.
61.4 K. Let's go to step number 9. What was the demand for heat cool? 300 K. Let's go to step number 11. What's the demand for fasten in place? 173.3 K. And the last one is for motors, which is a 12 K. Any question, guys, about these? I put them here so I can add them. I'm going to add them. So what do I need to do? Add them. Add them up. I don't want to use this color. I'm going to use this. I'm going to add them up. And right in here, who's my favorite student who's going to add them all up for me? 673.2 kVA. And this is your final number. Final number. This is the demand load for the whole building. That's how we're going to size the feeder, the disconnect, the panel. Everything is going to be sized based on this number. Any question, guys, before we move ahead with any question? I'm going to do the calculation for the neutral in a second. Let me just finish calculating the size of the service equipment panel, and then we'll do the service conductor in a second. Any question, guys, about these? Just add them all up. Let me go. I'm going to give you a break in a second. Let me go to step number 16. 16 is service entrance equipment, disconnect, overcomplication device, and conductors. I need to size the service the size of the panel. Here's how you do it when you go size the size of the panel. So number one, I equal, what was the total size that we guys came up with? 673.2 K, right? Right?
Yeah, that's right. Yeah.
Divide by 240. Why 240? The voltage system is 240, right? You came up with 2805 amp. Any question, guys, about that? I need to size the service. I need to size the service. Okay? So here's the amp that I did. So I need to size a few things. Number one, I need to size equipment. Panel size. For the panel size, guys, you're going to take this number 2805, take it to D wall for panel size. By the way, everybody knows what the panel size is, the copper inside the panel. The copper inside the panel. So take the panel size. D wall, what was the size? 3-12, page 3-12. 3-12. Okay. So can you guys go to 3-12, and what was size that we came up with? 3-12. Actually, you can't get it in 3-12. It has to be switch gear because panels go all the way up to 600. So we're going to go to switch gear design, and switch gear design, it's a single phase. So what's my next standard? 2500. Everybody got that one? Right here should be actually 13, not 12. 13. So I have to have a switchboard at single phase of, I have, my option is 25 or 20. No, you have 280. 25 is not going to make it. So you have to go to the next standard. What is it? 3000. So I have 3000 amp. That's the size of my panel. That's the size of my panel. Can I have thumbs up, Chad? We know what the size of the panel is? Yes, sir. Oh, I thought you were. The last thing, guys, overcurrent protection device. Overcurrent protection device. That's the fuse ahead of the panel. The fuse ahead of the panel. So I'm going to take the 2805 amp. Take it to where? Anybody knows where we go? 240.6. And what's the standard, Sir Bryce? 3000. So we hit the jackpot. 3000 amp. So the size of my fuse or circuit breaker and the size of my panel match. Match. The size of my fuse or circuit breaker and the size of my panel match. Both of them match. Any question, guys? Any question about that? Yes, sir.
In the event that they didn't match, you would want the panel to be bigger than the fuse, or the fuse to be bigger than the panel?
Always the panel bigger than fuse. Thank you. Good question here, Jeff. What if they don't match? Do you want the panel to be bigger than the fuse or the fuse bigger than the panel? Always the panel bigger than the fuse. This should be a 400 amp panel here. I can put a fuse or a circuit breaker ahead of it or inside it as high as 400, but not higher than 400. Does that make sense? I can put 200 amp on a panel that's bus copper inside it is 400. Everybody knows that? Okay, why don't we take 5 minutes break, and I'm going to size the conductors, including the two hots and a neutral. I'm going to do the rating neutral. I'm going to show you how easy to do the rating neutral all through. Okay, 5 minutes. Go ahead and start, as I said. So if you guys want to draw a little bit of a sketch for you like this, so this is what we're trying to achieve. The whole load calculation, Darren, is to you come up with a panel size, an overcurrent protection device inside the panel, which is typically the same size, the conductors coming to the panel, and the neutral, because the neutral, we have to derate the neutral. You're going to find.
That's
cool?
The main center, or what?
The what?
Main panel right there.
That's the main panel.
Yeah.
That's your main panel.
Yeah.
That's going to feed all these loads inside it. Okay? All right, so if you guys want to draw that one, And I'm gonna go back when you sketch that one. So that's basically what what we're trying to achieve. We're trying to size the panel. Exactly, Jeff, what we did, we sized the panel 3,000. The overcomputation device was 3,000. Now we're going to size the conductor to feed a 3,000 amp panel and the neutral to feed 3,000 amp panel. So, okay, having said that, let's go size the neutral before we move on. Here's my 15. Okay, so I sized I'm going to put, this one was, let me just say, the panel was number 1, right? So that was number 1. The overcomputation device was number 2. These are the two numbers I sized. I'm going to go size the conductors. So number 3, let's go to conductors. Number 3 is the conductors. This is again number 3. We're sizing feeders. In this case, it's going to be service intrinsic service. Let me use the term for it, which is service. Oops. Service entrance conductor. Service entrance conductors. Service entrance conductors, and this will be the 2 hots. Can you guys write yourself 2 hots? Not the neutral. The 2 hots, not the neutral. The 2 hots, not the neutral. We're going to size the neutral in a second. Okay. Here's what I would say, always say, guys, when you size a panel like this, match the overcurrent protection device. Match the overcurrent protection device. So the first thing you're going to write to yourself, you're going to say match overcurrent protection device. And why do we match overcurrent protection device? Match the overcurrent protection device from Article 220, 240. Which one is the? So we're going to match the overcurrent protection device. Okay, over 800 amp. This will be, your reference will be 240.4 B. Can you guys write your reference here? 240.4 B. This is your reference. It says if Jeff, it says if your overcurrent protection device is above 800, then the conductors, you have to match the overcurrent protection device. 240.4 B. Okay. So what's the overcurrent protection device? What's the size of the overcurrent protection device that I have? I have 3,000 amp. Now, can you find a conductor for 3,000 amp? For, is it C? 4 over, yes, thank you. C is B, you're absolutely right. C is 1 over. Thank you. C, 240.4 C will tell you if you're over 600 amp, over 800 amp, you have to match the overcurrent protection device. Okay, now can I find a conductor, guys, that can carry 3,000 amp? Can I find a conductor that can carry 3,000 amp? I can't find a conductor that can carry 3,000 amp. So what do? Parallel. Everybody heard the word parallel? You can't parallel less than 1 aught, and you have to parallel your conductors. So you're going to come up. I decided to parallel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I decided to parallel 10 runs, 10 conductors. Cool. When we have to size the conductors. When our overcurrent protection device is over 800 amp, like I said, you have to match your conductor, have to match the overcurrent protection device. I have a 3,000 amp overcurrent protection device. My conductor have to match it, right? I can't find a conductor over 3,000 amp. So what do I need to do? Did I hear the word parallel? You need to parallel. How many sets? That will set you to the commercial, guys. 10. Can I parallel 12? Yes. Can I parallel 15? Yes. When you parallel conductors, guys, your goal is to get a smaller number of parallel as you can. Okay. So we're going to go parallel. I decided to parallel 10 conductors. So if you divide this by 10, what do you get? 300 amp. If you take this one to table 310.15 B16 under 75-degree column, How many sets you have? When you parallel them, how many, what's the size? What's the size that you can come up with? 300 amp,
75 degree.
75 degree,
You're looking at 350 kc.
350 kcm. So I have two conductors, 350 kcm. Two conductors, 350 kcm. Two conductors, 350 kcm. So what I did here, guys, I did a graphic for you. This is when you parallel them. That's how it's going to look like. It's going to look like 10 conductors, 10 conduits. Each one of them is going to have 3 conductors. One of them is the blue and the other one is the red. The blue and the red are the two hots. Each one of these blue and red is going to be what size? 350. It's going to be 350 size. Any comments, any questions? So Adam, Joe, and Andrew, what we did is we sized the, when you guys were not here, we sized the conductors. When you size the conductors, you match the conductor to the overcap protection device. Since we can't find a conductor 3000 amps, so what do? You parallel them. How many sets? I picked 10. Could you have picked 8? Yes. I will tell you guys when we go to the commercial the best way to pick. I'm not going to open this can of worm right now. Okay. So I have, so everybody can see these conduits that you can find here. These are 10 conduits. Each one of them have 3 conductors. Each conductor, guys, have a size of what? Each conductor have a size of 350 kcm. What insulation, if you want to put an insulation, since these will be underground, probably, you're talking about a THHW insulation. THHW insulation. Now, up to this point, therein we're done. We sized the overcap protection device, and we sized the panel, and we sized the feeders, the hots, the 2 hots. What's the only thing that's left? The neutral. Now here's what, Joe, here's what I can do. I can say, Chad, the heck with you, I'm going to go use another conductor neutral here and make 3 conductors, 350 each, and call it a day. Cool? So here's what some engineers do. They go, well, I'm going to have full neutral. They call it full neutral. And they come over here and they carry, instead of carrying 2 conductors, what do you carry? 3 conductors. What we're going to do, guys, is we're going to size the neutral. And that's where I'm going to take you step by step how to size a neutral, which is very easy. So if you do me a favor, we're going to go size a neutral. I want, if you guys, if you wrote the steps that I did, I'm going to go back to step number 1, write in green. Everything I write in green is going to be related to the neutral. And tell you how easy it is to size a neutral. How easy it is to size a neutral. Any question about what we've done? We sized the panel, the overcap protection device, and the hots. Now I'm going to go back and size a neutral. The code says, guys, the neutral have to be sized to carry the unbalanced current between the 2 hots. So anything, any load that's 240, what's going to happen to this load when you size a neutral? Open the window, throw it out. So if you do me a favor, guys, here's what I drew for you. Okay, so we size number 1, 2, and 3, which is basically the cables, the overcap protection device, and the panel. I need to size number 4, which is the neutral. To size the neutral, here's what I'm going to do. I'm going to go back. Can you guys go back to this example, to the beginning? This is what I gave you. When we size a neutral, anything 240, you throw it out the window. So let's go ahead and step by step. Can you guys go to step number 1? Step number 1. Go all the way for your calculation to step number 1. Okay. Do you guys agree with me that general light is 120, so it should be included? Yep. How do you guys, by the way, anything related to the neutral, I'm going to use the color green. Right on this calculation. See how easy that is? Right on the calculation. Do you guys agree with me that 1, 3, and 4, the laundry, the small appliances, and the general lights are actually 120 loads? They're lights and receptacles, right? Can I have thumbs up, Chad? So these are all count as a neutral load. So I leave him as is. The only thing, okay, then up to number 6, here's where, up to number 6, this is where I'm going to write, I want you guys to put a star next to step number 6. right? Green star or something. This step actually that encompasses all the things that are ahead of it with the demand apply to the neutral, because the laundry, the small appliances, and the lights are actually neutral load. You guys understand what a neutral load is? Anything connected 120. The lights are 120. The receptacles are 120. Okay, so do you guys agree with me that this bunch of load here, 70.2 kW, is all going to be a neutral load, right? After you apply all the demands, everything as is, this will be a neutral load. So all what I want you guys to put here, put N for neutral, and this is the same number, 70.2 kVA, which is exactly the same number right here. So this will count as a neutral load. Can I have thumbs up, Chad? We clearly understand why. So we did all the calculation in it, we derived it, then it counts as a neutral load. Any question guys about that? So all the way 1 through 5, all of them are neutral load because they're connected to the neutral. Look at that. General lights, 120. Two small appliances, circuit, 120. Laundry circuit, 120. We apply the demand factor, and 70.2 kV is a neutral load. Can I have thumbs up for step number 6? So the first thing you need to carry then, we need to carry here for the neutral is this number. I need to carry this number for the neutral. I need to carry this number for the neutral. Cool? All right, so let's go to the next step. Okay, step number 7. Step number 7. So we got step number 7. Okay, let's look at the range. You guys remember what the code says about the range? Article 220.55 and 220.61. If you guys look at Article 220.61, Article 220.61, it says for the range. When you guys do a range, the neutral count as, anybody remember? 70%. Thank you, 70%. So here's for the neutral, N is for the neutral, and the load is going to be, take the 56.3 K, slam that baby by 0.7, and that will get you what? 39. That will get you 39.4 kVA, and that's my neutral load. This is the number that I'm going to carry for the neutral. Anything green is neutral. Can I have thumbs up, Chad? We understand for the ranges, the neutral load for the ranges, the neutral load is actually 70% of that number, 56.3. Questions, guys, about that? Where did they get this number from? 220.61. 220.61 will tell you have to derate. You can, not you don't have, you have to. You can derate 70% of the neutral for all the ranges. Anybody knows why? Because highly unlikely that everything is going to be connected to the neutral in every range. And to be precise, this will be B. Okay, any question guys about this step? Can I go to the next step? So see how we're doing calculation step by step for the neutral. Exactly what you guys are going to be doing. Any question about that? Can I go to step number 8? Can we do 8? Andrew? 8? Joe? Brian? Zach? Okay. 8. So let's go to step 8. Step 8, dryers. How do we do the neutral for the dryers? The same thing, guys. If you go to 220.61B, 220.61B, here's my neutral. It says 61.4 K. You have to multiply it by what? Who's going to get A on participation? 70%. 0.7. What would that give you? 43.
40, yeah.
3 kVA. This is the number. This is the number that you have to carry for the neutral. This is the number that you have to carry for the neutral. Where did the 70% came? Where did the 61.4 came? Right here, guys, 61.4. But I just cut it by 70%. Why do I do that? Even though these are 240 loads, because the 220.61b tells me to do so, and because the dryers have a 4-conductor, 3-conductor cable going to them. Any comments, any question about step number 8? Zach, makes sense? This is what you guys are doing for me for the load calculation. That's exactly what we're doing for load calculation.
You're cutting it to 70%, not by 70%.
You're multiplying about 70%. Yeah.
So you're cutting it
Down to 70%. Yeah. Yes, I see what I mean. You're cutting it.
If you cut it by 70%, it's going
I
to
see.
be gone into
Yeah.
like a 50.
You are demanding it by 70%, meaning you're taking only 70% of it. You're using 70% of it.
Taking it to 70%.
Okay, so that will be it. Shall we go to 9? Big difference, absolutely. Shall we go, guys, to step number 9? Step number 9. Okay, take this. Step number 9, heat and cool. Can you guys, anybody can guess? I have heat and cool. Both the heat and the cool are 240. So what do you guys think the neutral here would be? Big fat 0. So N stands for the neutral. This is going to be big fat what? 0 kVA. And that's what you need to carry when you take down upstream. Anybody knows why 0? Because everything is running at 240. All these loads that you're looking at here, these are 240 volt, 240 volt, and no neutral. There is no neutral. They're all running at 240. So they will not contribute to the neutral. Does that make sense, guys? They will not contribute to the neutral. If you guys understand the load calculation, now it will be easier in the commercial industrial. We'll repeat the same thing as we move forward. Any question about step number 9? Why the neutral is 0? Why the neutral is 0? Why the neutral is 0? Okay. So let's go to step number 11. How about 11? Now 11, there's a few things that you have to do for 11. Okay, I want you guys to wake up for 11. This load is 120 volt. This load is 120 volt. This load is 240 volt. Okay, so which load do you think, guys, is going to count? Thank you, the first two. So this will count, this will count, this will not count. Okay, so here's what I'm going to do. Then I'm going to take 1.25 times 30. Same thing, 1.25 times 30. This will be 0. And add them up. Can you guys see that? Same calculation. Same calculation. And anybody came up with 81? 81 kVA. Anybody came up with 81? Cool. Anybody knows why we put 0 for this, the third one? Because they're 240. They don't contribute to the neutral. Yes, sir.
Okay, okay, so it's 1.2 and 1.5
Yep.
times 30. Okay, because you wrote 1.2 over there, and you said 1.25 when you wrote it. So
1.
so it's the same numbers that you had on the.
Thank you.
Okay.
1.5. Thank you. 1.5, 1.2 and 1.5. You're absolutely right. We're just carrying it here. We're not doing anything.
Yeah,
Thank
well,
you.
and you said 1.25 when you wrote it, so.
Gotcha. That's mistake. My mistake. Okay, 1.2 times 30, 1.5 times 30, add them up to 81. Can I have thumbs up, Chad? They add up to 31. Okay. All right. Then you're going to apply the demand. You're going to take the 81K and multiply it by 0.7, the same way, 75. And that will get you 61. Can I have a 61 kVA? 61 kVA. And Adam, my friend, this is the step that you're going to carry downstream. This is the step. The green one is the step that you're going to carry downstream. Guys, we're repeating the same calculation for the neutral. Anything 240, we're throwing it out the window except the ranges and the dryers. We're taking them at 70%. That's exactly what we're doing. Any question, guys, about what we did here? So, Aaron, my friend, the reason why we dropped the water heater from this calculation, because water heaters are running at 240. We're telling you it's running 240. So it contributes as 0 to the overall of the neutral. Can you have thumbs up, Chad? We fully understand that?
Is it only the fastened in place appliances that you do the,
So, yes. Yep, absolutely.
so it wouldn't be anything like if you had a indicated circuit for a microwave or anything like that? Would that
If you look at other, yeah, a lot of people use, if it's a fixed in place microwave, they give it the size of the microwave dedicated and apply it to it. Yes. Yes.
What's the code reference for the 75% D-rate?
75% is 220.53, right here.
So it's the same.
Same thing.
chapter as the-
Yep. The code reference 220.53. Okay. Everybody knows that this number here will be carried down, guys, downstream later on. All right, let's go to step number 14. Step number 14, guys, is motors. Now, Joe, my friend, the motors are all running at 240. Do you think they're going to contribute the one motor to it? So, no problem, Chad. So, what is the neutral? N for neutral is going to be what?
0.
Big fat 0. KVA. Done. And that's what you're going to carry upstream when you do the calculation. You're going to carry nothing. 0. Can you just see the rhythm, Zach? Does it make sense? You see the rhythm of the whole deal? So 240, it's not going to contribute to it. Cool? We're done. We're done. Now we're going to go add them up as a neutral. Okay, so here's what I'm going to do, guys. I'm going to put the neutral right here. I'm going to put the neutral right in here, okay? So let's go start with the neutral. 70. The first for the neutral, it's 70.2K. Anybody disagree with step number 6? It continued to be the same, right? How about the ranges? The ranges, it's 39.4K. Everybody knows where we got the 39.4K because the ranges we multiply by what? 0.7. Okay, how about the dryers? The dryers, when we carry for the dryers, 43K. How about the heating? Big fat K. How about the heating cooling, right? Big fat K. Right? How about fasten in place? 61K. Right? 61K. How about the motor? Big fat K. And you add them up. Any question, guys? Yes, sir.
What about, I guess this could wait till after you're finished with everything, but I was just curious about the motor load for the neutral if you had 120 volt loads.
Then you add them up.
Okay. Then you still do the take
125%. Yes.
Yeah.
Yes, absolutely. Absolutely. Any question, guys, about this example? Everybody knows where we got these green numbers? Any question how we got them, why we got them? Okay, so add them up. When you add them up, you end up with 214. Anybody disagree? 2140 kVA. And this is the number that you're going to carry to size your neutral. This is your demand for your neutral. Can you guys see the difference between the neutral demand and the phase demand, the hot demand? We went from 673 into 214. Can you guys see the gravity of that situation? Huge. Okay, now let's go size and neutral. Before I go here, guys, any question about these? That's what you guys do the load calculation. I can't emphasize. You're going to do it for me this quarter, this project, next project, and the project after. You get it now, you're done. If you don't get it now, you have another 2 chances to get it. So we're going to do the same calculation. Believe me. The only thing, Jeff, that we're going to change in commercial, we're going to move to 3-phase. That's all. We're going to, every load is going to be 3-phase. Okay, so let's go size and neutral. Okay, neutral. So I'm going to go directly and size my neutral. Now, number 4. I want to have my neutral here, which is number 4. Remember that neutral was number 4? Number 4. What was the kVA for the neutral? 214. 214 K. Divide this by 240. Why do we divide by 240, not 120? Anybody can give me why do we divide by 240, not 120? So it's because they're going to be balanced. It's going to be balanced, right? It has to be balanced. We divide, even though it's a neutral load, 120, we divide it by 240 because half of them, well, we are hoping half of them will be in one hat, the other half on the other hat. Anybody can come up with the number, the answer here? 800.
91.66.
92 amps, 892 amps. 892 amps. Okay, now, any question guys about this? All right, now take this one to, now I need to parallel. 892. Now I need somebody to help me. The code says, Adam, if you parallel the hots 10 sets, do I have option of how many sets to carry? You're stuck. If you parallel the hots, if your hots are parallel 10 sets, then neutral must be parallel 10 sets because you have to carry the hots and the neutral with every set. Do you guys see that? If you pull 10 sets for the hot, you must pull 10 sets for the neutral. So do I really have any option here to put 9 sets or 11 sets? Or so this will be 10. So that will give me what? 89.2 amps. 89.2 amps. Cool? 89.2 amps. Yep. All right, so let's go size the 80. Now we're going to go size it. 89.2 amps. Take this one to table 310.15 B16. B16 under a 75-degree column. Because if the hots are 75, the neutral have to be 75. So what size would you guys come up with? Number 3. How many? 1 conductor. Number 3. AWG THHW. Okay, up to this point we're done, except there's one little problem. Up to this point we're done. The neutral is going to be number 3. There's one little tiny problem. The code says if you're paralleling, you can't parallel less than number. Anybody remember? Number 1 odd. So that's the only, you're done. Up to this point, you're done. But because I'm paralleling, I can't parallel a conductor for power less than number 1 odd. Can I have a thumbs up, Chad? That's what the code says. So because of this, my neutral conductor is going to be 1 conductor number 1 odd AWG THHW. And can you guys write yourself here the reason for this paralleling? Because of paralleling, you can't parallel less than 1 knot. You can't parallel less than 1 knot.
What section is that in?
That's what I'm trying to find it. I thought I got the message for that one. They flipped them in 2000. I'll find it for you. It's 3. It wasn't 300. Okay, so take my word for it until I find it for you. Okay, I found it.
250?
No, 310.10H. Here's your reference. I know you guys don't believe me until I put a reference here. 310, the reference for this one is 310.10H. Can you guys guys write this reference for you? 310.10H. If you guys go to 310.10H, it tells you 1 aught is the minimum that you can pedal for any conductor, hot or not hot.
That's new, this NBC code.
It was really nothing new, but they shifted it, they rearranged it, but it's not new though.
Change it and confuse us.
Yeah, they shifted them where they were. It was in a different location. That's why it took me a little while here. I should remember because I've been teaching it for a while. Okay, so before I leave, can you guys see what I did here? I have 10 sets, Joe, 10 sets of conduits, 10 conduits. Each one of them has 3 conductors, 2 hots and a neutral. The 2 hots are 350 and the neutral is what? 1 off. So if you guys, I don't know, or let me see. So if you want to come here, this will be my 1 aught, and these 2 guys will be the 350 kcm. Can you guys see that? 1 aught and 350 kcm. I need somebody to give me a thumbs up, Chad. We fully understand that, what we have done. Now look at that. You could have carried 350 and lost the project, Joe, when you bid on it, right? Imagine 350, guys. Look at this, 350 times 10. 10 conductors, 350, multiplied by at least probably 100 feet. See how much copper you did versus what? 1 aught. Now the building burned and you did this calculation, you went to the court and you did this calculation, your chances of winning the case is much higher than if you did not do the calculation. So that's basically what the neutral is. So my conductors will be 3 conductors, 2 of them is 350 and 1 is 1 aught. For the neutral, I have one little thing for the neutral I'm going to add, guys, for you before I let you go. For the neutral, if you guys look at 250.241, 250.241 for the neutral, and you have this one in the sheet that you guys have, the code also says for the neutral cannot be less than the main bonding jumper. If you go to 250.241C, it says you can't be less than the main bonding jumper. Okay, so let's go size. This is again, we're talking about neutral here. Continue with the green here. Talking about my neutral. My neutral. Okay, so to find the main bonding jumper or system, main bonding jumper, and we're going to go through this one in details, guys. We'll do it in details. So you're going to hear Chad talk about it. To size this one, this is how we size it, guys. You take 10 times 350K, that will give you 205.00 kcm. This one from table 250.66. 250.66 and article 250.28. These 2 tables in this article. Then you take 12.5% times 3500K. That will get you 438 kcm. Okay, and then you take the 438 kcm, you take it to table 8, chapter number 9, and that will get you 500 kcm. This is the main bonding jumper. I promise you we'll talk about this in details. I don't want to emphasize it that much, but the reason why I throw this one here, because the code says the neutral, no matter what you come up with, the neutral shall not be less than the main bonding jumper. So then look at this. What's the neutral? The main bonding jumper is 500. What's the size of the neutral? 1 aught. Am I in trouble? Am I in trouble with this code requirement? Okay, before you answer this one, how many 1 aughts do I have? Okay, so let's do this check. And if you get this one, you're going to run into the commercial industrial like a lion here. Okay, so to check if we're in trouble or not, can you compare 500 kcm to 10 runs of 1 aught? You can't. You have to convert them to the same language, which is KCM. Here's what you're going to do. So take the 10 runs. How many runs do I have? I have 10 runs. Okay, for 10. Multiply this one. What's the KCM for 1 knot? Can you guys go to table 8 and find the KCM for 1 knot, please? The KCM for 1 knot. From table 8, KCM for 1 knot. Anybody's there? Where's my A students? Table 8, chapter 9. Got him?
105,600.
Give me the number.
105,600.
600.
Circular mills.
105000. Okay? Right?
That's 105,600.
105600. Gotcha.
105,600.
Okay, multiply this by 10. That will get you 105, comma. How many zeros? 1, 2, 3, 4. 1, 2, 3, 4. Right? Did I do the math right? 1, 2, 3. No, 3, check. Not 4. 3. Okay? Right? When you multiply by 10. 105.
Maybe one more zero.
Should read 1,056,000.
1 second. 1, 5. And there's a 6. And 0, 0, 0. Right? This is how it reads. Did you do the math right? 105600. Right?
Yep.
Okay, now this will translate into 1056 KCM. Right? Is this bigger than 500 KCM? Am I good? Yes. Do you see how you, for a second, you look at the 500 and the 1 knot and you say, no. But remember, there's 10 1 knot. When you take the 10 1 knot, compare them to the 500 KCM, you are much higher. Right? So am I good based on this? Yes. Any comments, guys? Any questions? Main bonding jumper, system bonding jumper, and all this good stuff is coming. The more you get it now, the better you will be in the future. Any comments about this? So if you get that one, I didn't want to emphasize too much of it. It's coming. I just want to get you an idea that when you do the neutral, you have to always do this check. So we are doing good here based on that check. Anybody knows why the main bonding jumper, they don't want it to be smaller than the neutral? Because remember, the main bonding jumper is right here. If we go back, here's the neutral. Here's your ground. This is G. This is the grounding electrode conductor. The main bonding jumper, guys, is this wire between these two. Right? This is the main bonding jumper. So the neutral have to be grounded to the grounding bar. So they want that main bonding jumper to be at least the neutral as large as the main bonding jumper. So your system is fully grounded. Your system is fully grounded. Again, I have a lot of sheets, guys, about grounding and bonding, so I don't want to make it grounding and bonding for the time being. I just will make you to understand the 4 things that we size. Can you have thumbs up, Chad? We fully understand how to size the following. Number 1, the panel. Number 2, the overcome protection device. Number 3, the pots, aka the phases when we go to 3-phase. And number 4 is the neutral with the rating. So looking at adding, this is my 3000 amp, 240 volt / 120 volt. This is a 3000 amp, and the conductor here are 10 sets. This is how you guys write them. 10 sets, right? Of how many conductors? 2 conductors. Number 350 KCM. THHW, and 1 conductor 1 at AWG That's what engineers do. When you're done, that's what you size. You size the overcap protection device 300, 3000. The panel itself is 3000, and the conductors are 10 sets. You know what 10 sets are? Conduit, 10 conduits, 3 conductors in each conduit, 2 conductors of about 250, and 1 conductor is 1 out. Okay. We did not size the main bonding jumper, as a matter of fact, came here to be 500 kcm. That's a 500 kcm. One 500 kcm main bonding jumper, that little connection. I didn't ask for it, but we sized it for 500 kcm. Any question, guys? Any comments? Can I have thumbs up, chat? This is enough to get us to size for dwelling. Now, I can't emphasize. We're going to do the same thing for commercial industrial, guys. You get it now, you got it. You don't get it now, you got 2 shots at getting it. Make sense? Because I'm going to repeat myself the same thing for a 3-phase system. The only thing, Aaron, that's going to change, instead of the voltage 240, 120, I want to make a voltage 28, 120 for one project, and another voltage 480, 277. So the only thing is going to change. And a few things added, more loads. Bix more expanded, but really the process is the same. So get it now or get it later. Cool. So any comments, any question, guys? Okay, I want to give you guys 5 minutes, and I'm going to show you what to do for the site, and then I would like to do red lines. Thank you.